Hello and welcome. This section is about finding the maximum flow in a flow network. We will first look at what it means when we refer to a flow network and what maximum flow means. Then we'll walk through the two algorithms which work out this maximum flow in a network. So let's first get started with this video and describe the problem. In this video, we will first explain flow networks and then discuss what we mean by maximal flow through the use of examples. Later, we'll explore some practical applications where determining the maximum flow would help solving the problem. A flow network is a directed graph in which each edge can receive a flow not exceeding the capacity of that edge. The capacity of an edge is shown in this example graph. Each node in the graph outputs the same amount of flow as its input. The only exception to this is the source and sink nodes. These are the nodes marked with letter S and T respectively in the diagram. Typically, a flow network graph will have multiple paths from source to the sink node. Let's have a look at a more complete example so we can understand flow networks and the maximum flow better. Imagine you are running a rail network company and there is a particular station which has a bit of a problem. This is the station that serves the local small airport. The airport is quite remote and is far away from the train station. The problem is that there is no easy way for train passengers to get to the airport. Their only option is to take a series of bus connections. There are various routes and options for the passengers through the various towns and bus changes. Each connection has a capacity flow limit. For example, this particular connection can typically take about 8 passengers every 15 minutes. You have collected this flow capacity for every bus connection. What you see here is an example of a flow network. The train station is the source, where it's introducing flow into the network, in this case, the passengers. On the other side, we have an airport, which is our sink, accepting the passengers and putting them on a plane. As a train company, we want to determine the maximum number of passengers that this network can accept before it becomes full and unable to accept more, resulting in queues at the train station. This is called the maximum flow of the network. Using this max flow, we can then plan ahead and decide how often we schedule trains. There are many other similar scenarios for flow networks. For example, in computer networks, we can determine the packet flows from a server to a client. And in real life, we can use flow networks to model water distribution, or electricity in a circuit using current as a measure for capacity and flow. Basically, we can have a measurable flow network whenever we have a flow from source to a sink, and each node doesn't leak any of that flow. We can represent this flow network programmatically by modeling this as a weighted graph data structure, labeling one of the nodes as a source and the other one as a sink, and the rest as intermediate nodes. There are many applications for finding the max flow in a network. Typically, the algorithms work on a single source to a single sink network. However, they can be adapted to be used in a multiple source to sink one. Consider this graph as an example. Consider this example flow network where we have multiple sources and multiple sinks. To this, we can just add a single source master connected to all sources and a single master sink connected to all outputs from all the sinks. We can then use the same algorithms to determine the maximum flow. This allows us to extend the maximum flow algorithm to a wider range of applications. The algorithm can also be used to solve another type of problem called bipartite matching. Let's have a look at an example of this. Imagine we were responsible for allocating student accommodation. we have several empty dorms to allocate to students. Some of them are single bed, and others have 2 beds. We have the same number of students as beds. However, students are allowed to provide dorm preferences. This particular student, for example, would prefer to stay in one of these double rooms if possible. So different students send each their own dorm preferences. Now it's up to us to find an allocation that would keep the largest number of students happy. One way to do this is to model each student and each dorm as a separate node in a graph. The student and dorms are connected by an edge, modeling the preferences they provided. Each edge would have a capacity of 1. In this image, we're only showing this once to reduce clutter, but every edge connected between the student and the dorm should have a capacity of 1. We then create a sync node to one side and connect every dorm to it. For the rooms that only have 1 bed, we can have an edge capacity of 1, while the rooms with 2 beds should have a capacity of 2. On the other side of our graph, we should create a source and join it to each student node. Each edge here should have a capacity of 1. Again, we're only showing one edge to reduce clutter. If now we use the maximum flow algorithm on this graph, it will tell us the maximum number of people we can make happy, and also the allocation we can use. This type of problem is an example of a maximum bipartite matching and has many other practical applications. The name bipartite comes from the fact that the graph is split in 2. A node in the left part of the graph only connects to the right part of the graph. In this video, we have examined various examples and applications for flow networks and finding maximum flows.